Have you ever wondered how the CPU accesses operands for instructions? Well, that's what we're going to delve into today. In the realm of computer architecture, we use a concept called addressing modes to define this very process. An addressing mode is essentially a formula that the CPU uses to calculate the effective address of an operand based on certain parameters. The beauty of these addressing modes is that they offer flexibility in accessing data in different ways. Throughout this video, we'll be exploring various types of addressing modes such as immediate, register, direct, indirect, base register, indexed, relative, base register plus index, and even memory indirect addressing. Each of these modes has a unique way of accessing the data needed for CPU instructions. Now that we have a basic understanding of what addressing modes are, let's dive deeper into each one. First up is immediate addressing. This is where the operand is a constant or an immediate value specified in the instruction. Immediate addressing mode is like the straight line of addressing modes. No frills, no detours, just direct and to the point. Imagine you're given a task to move a box labeled 5 into a specific storage bin. In the language of computer architecture, this would be akin to the instruction MOV AX 5, where MOV stands for move, AX is the destination register, and D5 is the immediate value or the box you're moving, so you're directly moving the value 5 into the register AX. This mode is particularly efficient when working with constant values, as it eliminates the need for extra memory accesses. So immediate addressing mode is straightforward, isn't it? But what if you want to access an operand located in a CPU register? That's where register addressing comes into play. In this mode, the operand is located in a CPU register. Think of it as a shortcut to quickly access the data you need. Instead of searching through the entirety of your computer's memory, the CPU can simply go straight to the register where the operand is stored. Let's break it down with an example. In x86 assembly language, you might see an instruction like add AX, BX. What's happening here? The CPU is adding the contents of register BX to register AX. This is a prime example of register addressing in action. The CPU swiftly grabs the operand from the register, performs the operation, and moves on to the next instruction. So, in a nutshell, register addressing is all about efficiency. It's like having your most used tools in a toolbox always at hand instead of scattered around a workshop. With register addressing, we can directly access operands in CPU registers, but how about accessing operands with explicit addresses? Direct and indirect addressing modes are what we use for this. In direct addressing, the effective address of the operand is given explicitly in the instruction. It's akin to being handed a treasure map with a big, bold X marking the spot. For instance, in x86 assembly, we might see something like MOV AX. This command tells us to move the contents of memory location 1000 directly into register AX. As simple as that. Now let's consider indirect addressing. Here, the operand is pointed to by the contents of a register or memory location. So instead of an X marks the spot situation, you're given a clue to where the treasure is. You'll need to follow that clue to find your treasure, or in our case, the operand. Let's look at an example. In x86 assembly, you might see MOV AX. This is saying, hey, the address of my operand is stored in BX. Can you go fetch it for me, please? So, you go to register BX, find the address stored there, and then fetch the operand from that memory location. Essentially, you're following the clue in register BX to find your operand. Both these addressing modes offer their unique advantages. Direct addressing is straightforward and uncomplicated. The address is right there in the instruction, no extra steps needed. It's great when you know exactly where your operand is and you just want to fetch it. Indirect addressing, on the other hand, is a bit more flexible. It allows you to use the same instruction to access different operands, just by changing the contents of the register. This can be extremely useful in situations where you need to work with a range of data stored in different memory locations. Through direct and indirect addressing, we can access operands located in specific memory locations. But what if we want to form an effective address by adding a constant to a register's contents? For this, we use base register, indexed, and relative addressing modes. These modes allow us to form effective addresses by adding a constant to a register's contents or to the address of the next instruction. Starting with base register addressing, the effective address is formed by adding a constant, known as displacement, to the contents of a base register. Consider the example, MOV AX. Here, we're moving the contents of the memory location at the address formed by adding 10 to whatever is in the SI register into the AX register. Next, we have indexed addressing, which is quite similar to base register addressing. The difference is that here, an index register is used instead of a base register. Let's take an example, MOV AX. In this case, we're moving the contents of the memory location at the address formed by subtracting 20 from the contents of the DI register into the AX register. Lastly, we have relative addressing. This mode is slightly different from the previous ones. Instead of adding a displacement to a register's contents, we add it to the address of the next instruction. For example, consider the command JMP label. Here, the program jumps to the instruction labeled label. The effective address is formed by adding a displacement to the address of the JMP instruction itself. Each of these addressing modes offers unique advantages. Base register and indexed addressing modes are useful when we need to access data structures like arrays, where elements are at fixed distances from the start. Relative addressing is particularly handy for jumps and branches in the program, as the displacement is relative to the current instruction, not an absolute memory address. These addressing modes provide flexibility in forming effective addresses. But what if we want to form an effective address by combining a base register and an index register? That's where base register plus index and memory indirect addressing modes come in. These modes allow us to form effective addresses by adding a constant to the sum of a base register and an index register. Let's start with base register plus index addressing mode. This method uses a base register, an index register, and a constant displacement to calculate the effective address. For example, in x86 assembly, you might see something like MOV AX. This means we're moving the contents of the memory location at the address created by adding BX, SI, and the constant 10 into register AX. What we've done here is use two registers to give us a wider range of memory access. BX might be a base register pointing to the start of an array, while SI could be an index register that steps through the array. The constant 10 is an offset that fine-tunes the memory location we're accessing. Now let's move on to memory indirect addressing mode. This mode is similar to base register plus index, but with a twist. Here, the address of the operand is not directly given by the base register and the index register. Instead, these registers point to a memory location that contains the actual address of the operand. Let's say we have an instruction like MOV AX. This double bracket notation indicates that the base register and the index register, along with the constant, are pointing to a memory location. This location holds the actual address of the operand that we want to access. So we first calculate the effective address as BX plus SI plus 10. Then we go to that memory location to find the real address of the operand. These addressing modes offer the most flexibility in forming effective addresses. But remember, each mode has its own use cases and advantages, whether you're stepping through an array, accessing a table, or dealing with complex data structures. Understanding these addressing modes will give you a powerful tool for managing memory in your programs. So we've covered a lot about addressing modes today, each with its unique features and applications. We delved into immediate addressing, where the operand is a constant value specified in the instruction. Then we moved on to register addressing, where the operand resides in a CPU register. We also explored direct and indirect addressing modes, which provide the effective address of the operand explicitly in the instruction or via the contents of a register or memory location. We touched on base register, indexed, and relative addressing modes, each offering flexibility in accessing data in various ways. And finally, we broke down the base register plus index and memory indirect addressing modes, which employ both a base register and an index register to form the effective address. Understanding these addressing modes will help you better grasp how CPUs access operands for instructions. Keep exploring, and you'll uncover more exciting aspects of computer architecture.